We studied direct current earlier. Direct current does not change direction with time. However, most appliances in our daily lives run on voltages and currents that vary with time. A time-varying voltage that varies like a sine function is called alternating voltage or AC voltage, and the current driven by it in a circuit is called alternating current or AC current. The term AC is actually universally used to refer to any electrical quantity that varies with time, just like simple harmonic motion that is related by a sine or a cosine to time. In circuit diagrams, AC voltage is denoted by a sinusoidal wave in a circle. Electrical energy supplied to consumers is transmitted and distributed through power grids as alternating current. AC is preferred to DC mainly because AC voltages can be easily and efficiently converted from lower to higher voltages and vice versa using transformers. Let us study what happens when an AC voltage source is connected in series to a resistor with resistance R. The potential difference provided by the AC source is expressed as V is equal to Vm sin omega t. Here, Vm represents the amplitude of the voltage and omega represents the angular frequency of the oscillations of the potential difference. Angular frequency omega should not be confused with frequency. For example, the AC voltage supplied to our households has a frequency of 50 Hz. This means the angular frequency is 100 pi radians per second. We can calculate the current passing through the resistor using Kirchhoff's loop rule. The algebraic sum of all the potential differences across various components in the circuit is equal to 0. A proper sign should be used for potential differences around the loop. Applying Kirchhoff's loop rule to the given circuit, we get Vm sin omega t minus IR is equal to 0, where Vm is the maximum potential difference offered by the AC source. Here, Vm sin omega t is the potential across the given voltage source. The second term IR is due to the fact that if a current of magnitude I passes through a resistor of resistance R, the potential fall across it can be denoted by the term IR. Solving this equation, we get the expression for current as I is equal to Vm by R into sin omega t. As the magnitude of the resistance of the resistor R is a constant, the equation is simplified to I is equal to Im sin omega t. Here, Im is the amplitude of the current denoted by the fraction Vm by R. The graph of the current passing through the resistor and the potential difference across it against time is as shown. Here we observe that the magnitude of the current flowing through the resistor and the voltage across the two ends of the resistor reach their maximum values at the same time. They also reach their respective minimum values at the same time. In fact, these values even reach 0 at the same time. This implies that in a pure resistor, the current flowing through the resistor is in phase with the potential difference across it. The fact that the current and voltage are in phase can be seen more clearly if we divide the instantaneous voltage V by the instantaneous current I. Therefore, the ratio of the instantaneous voltage V and instantaneous current I is a constant of magnitude R. This means that the ratio of voltage to current is constant. Hence, Ohm's law is valid in the case of resistances connected in a circuit with an AC voltage source. As the AC current flow across a resistor varies with time in a sinusoidal fashion, its magnitude takes both positive and negative values. Here, all instantaneous current values over a cycle add up to 0. Therefore, the average current is 0. However, the average power across the cycle is not 0 since the power dissipated across the resistor is proportional to I square. As I square always assumes a positive value even when the value of current is negative, the average power is always positive. We know that electric current refers to the flow of electrons in a circuit, and the direction of the current is conventionally taken to be the one opposite to the direction of the flow of electrons. As electric current passes through a resistor, the resistor gets heated. This is due to the collision of electrons with other electrons and atoms, and the constant acceleration and deceleration of electrons due to a reversal in the direction of the flow of current. This heat dissipation across a resistor due to the electric current through it is also known as Joule's heating, which is expressed as I square R. The instantaneous power dissipated in the resistor is I square R. Earlier, we learned that the current through an AC circuit containing a resistor is given by I is equal to Im sine omega t. On substituting the value of I in the equation for power, we get P is equal to Im square R sine square omega t. If we average the value of the instantaneous value of power over an entire cycle, we can write the expression as shown. Here, the quantity P bar denotes the average value of power. Conventionally, an average of values is shown with the bar over the quantity symbol. The angular brackets denote the average of the quantity inside the brackets. As the quantities Im and R are both constant, we can take them out of the angular brackets while computing the average value of the expression. Now, we have to calculate the average value of sine squared omega t in order to compute the average value of the expression. For this purpose, we will use the trigonometric identity. Sine square omega t is equal to half of 1 minus cos 2 omega t. Therefore, the average of the required expression is given as shown. However, the average value of cos 2 omega t over a complete cycle is 0. This makes the average of the sine square omega t over a cycle as half. Therefore, the average power dissipated over a cycle is half of Im square R. If we define a new value of current to be associated with AC, that is, Im by root 2, we can get the expression of power dissipated from a resistor in AC current in the same way as in DC current. That is, I square R. This new value of the current is called root mean square. In short, RMS current, denoted by IRMS or effective current. RMS current is defined as the root of the mean of the square of current. For a sinusoidal current, its value is 1 over √2 times or 0.707 times the amplitude of the AC current, Im. The average power dissipated by any form of AC current in a resistor is IRMS square R. Similarly, we can denote the RMS voltage or effective voltage VRMS as Vm by √2, where Vm is the amplitude of the AC voltage. The value of voltage normally used to describe an AC voltage is an RMS voltage. For example, domestic supply has 220 volts AC. Here, 220 volts is the RMS value of the voltage given to domestic consumers. The amplitude of the AC is √2 times the value of RMS voltage. Thus, the amplitude of the AC given to domestic consumers is approximately 311 volts. In our study of AC current applied to a resistor, we found that the voltage and current through a resistor are in phase, which is not always true. That voltage and current through a resistor are in phase was based on an assumption that there are only resistors in the circuit. Normally, circuits are made up of inductors, capacitors, and other elements. To study such complex circuits, where elements other than resistors are also present, computing values becomes an arduous task. Thus, we use the notation of phasors, which significantly simplifies the calculations involved in solving such complex circuits. A phasor is a representation of a sine wave whose amplitude, phase, and frequency are time invariant. We can visualize a phasor as a phase vector that rotates about the origin with an angular velocity omega. Thus, the phasor of a wave is a vector that has a magnitude equal to the amplitude of the wave and that rotates around the origin with an angular velocity equal to the angular frequency of the wave. To get the physical values of the sinusoidal varying quantities, such as AC current I and AC voltage V, we take the vertical component of the phasors, I and V, respectively. The magnitude of phasors, V and I, signifies the maximum or peak amplitudes of the quantities